Hyperfine splitting in exotic atoms. Quantum mechanics hidden gem. What happens when we swap out electrons for heavier or antiparticles? Find out how hyperfine splitting in muonic hydrogen, positronium, and muonium challenge our understanding of quantum mechanics. And here is actually a diagram from a actually pretty cool paper that kind of discusses all the different splitting that we see here and all the different corrections that we have to a muonic deuterium, I believe, with the fine structure, the Lamb shift, and then the hyperfine structure. So this is really cool and really small. Hyperfine clearly is the smallest of these order corrections. So let's check out what this is. In this problem, 7.32, we want, by appropriate modifications of the hydrogen formula, determine the hyperfine splitting in the ground state of A, muonic hydrogen, in which a muon with the same charge and G factor as the electron, but 207 times the mass, substitutes for the electron. Part B, positronium, in which a positron, same mass and G factor as the electron, but opposite charge, substitutes for the proton. And C, muonium, in which an anti-muon, same mass and G factor as a muon, but opposite charge, substitutes for the proton. And the hint he gives is, don't forget to use the reduced mass, problem 5.1, in calculating the Bohr radius of these exotic atoms, and use the actual masses in the gyromagnetic ratios. Incidentally, the answer you get for positronium, is this number, is quite far from the experimental value 8.4 times 10 to the negative 4 eV. Yeah, that's quite different. The large discrepancy is due to the pair annihilation. So that's pretty cool to see, which contributes an extra 3/4 delta E and does not occur, of course, in ordinary hydrogen, muonic hydrogen, or muonium. Ooh, some weird words. All right, so after reading that passage, why do we care about this? Well, the hyperfine splitting in exotic atoms is important for understanding the fundamental interactions. As we see here in a little hint, the pair annihilations make a big difference in the hyperfine splitting. So the challenge is, where do we observe this theory in practice? I'm sure some chemist out there might see something happen, or quantum field theorists can give more insight to this, but what do you think would be a place we would see this in practice? All right. Although this problem is kind of lengthy to talk about in the beginning, it's actually not too challenging. But again, I have all the relevant equations and little algebra work in the PDF, so feel free to grab that below. As a reminder, the PDF is free. All members can have it. Just grab it, download it, all the fun stuff. If you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No account required. All right, so enough of me yabbering. Let's get on to the fun. All right, so stop one then is, well, to go over this, let's make a game plan because we already have the delta E term that we want, and we can just modify that like they tell us. Modify the hydrogen equation, and then we can go ahead and move forward. How do we do this though? Well, let's recall that this is still a first order theory, and as such, the first order hyperfine, that should be hyperfine structure. Okay, we see that this comes in with the mu naught Gp e squared 2 pi mp, the proton, the electron, and the Bohr radius. And here you have the spins of the proton and electron. So we talked about with the fine structure that we had the spin-orbit coupling. That was one thing, and then the relativistic correction. So here we have to be careful because now, what if I have two things in orbit? Then I have a spin-spin coupling, or the proton has a spin, so now we have a spin-spin coupling, and that's what this represents here. Okay, and that's pretty cool to see. And of course, when we look at all the effects on the order of magnitude of their corrections, spin-spin does not give anywhere near what the hyperfine does or the Zeeman does So all of these are kind of ranked order, and as we saw in the diagram, the Lamb shift is really big compared to the hyperfine and fine structure. So you're probably going to have to dig a good bit to find this in any of your spectral diagrams. But nonetheless, what we see here and that we want to highlight is that we have that delta E is proportional to the G factor, okay? And then we have the masses in the bottom, but we want to keep those the same. But recall that the Bohr radius A, which sometimes denoted A naught, is proportional to 1 over the mass of the electron, which is stated by equation 4.72. Okay, so what the problem is saying is that we want to make this Bohr radius the reduced mass term and use that to calculate everything from us. So let's see how we do that. All right, so if we want to tinker with the mass terms, we want to modify the mass term via the reduced mass in the Bohr radius as we talked about in the last slide, but not the MP-ME term, which comes from the dipole terms in equation 7.89. That was the SP.SE. Okay, and both of those have a magnetic moment, and that's what makes it special and why we want to keep it there. However, to do this, we consider the ratio of the terms. Okay, so the reduced mass term, well, if I go ahead and realize that A is proportional to the inverse of M, the mass, then by taking the ratio, I can get rid of whatever the proportionality constant is. And we'll show exactly how that's done in the next step. But why is this reduced mass thing important anyways? Well, in systems where two particles are bound together, such as hydrogen-like atoms, the reduced mass accounts for the fact that both particles contribute to the overall motion. The reduced mass simplifies the two-body problem into an equivalent one-body problem, where single particles with the reduced mass moves in the potential created by the other particle. This is crucial for accurately determining the Bohr radius and other properties of the system. Here's why the reduced mass is necessary here. The relative motion in a bound system is with both particles orbit their common center of mass. We've kind of seen them in star systems and other equivalent systems. Newton's laws come to mind, Lagrangian mechanics, things like that. And so the reduced mass, mu, accounts for this by effectively reducing the system to a single particle moving in the potential created by the other particle. And we remember this from Physics 101, where when we drew a free body diagram, we drew it at the center of mass of the object, okay, regardless of where the forces were applying to. So pretty cool. All right, but enough rambling on the background. Let's get into setting this up and see why this ratio matters so much. All right, so taking the ratio of A with the reduced Bohr radius, we see that we get the formulas here given by equation 4.72, and dividing by a fraction means that we're multiplying by the reciprocal, and we see that all the constants cancel as you would expect in a ratio. And so being able to set up proportionalities like this are great when we're taking ratios because everything that would have been a proportionality constant cancels out. And so A over the reduced Bohr radius leaves me with the reduced mass over ME. And this will allow us to substitute into everything we need to find out how to modify the hydrogen equation. So that's why we do it, and let's see it in action. So this leads us to stop number 2, where we have the muonic hydrogen. So the things that remained unchanged in the question were the G factor, mass of the proton, and the charge. Cool, we got that. What did change though is the mass of the electron gets moved to the mass of the muon, and I'm trying to keep the notation the same because muons are typically denoted with the Greek letter mu, but so is the reduced mass, so it kind of gets a little hectic. But we are told that the muon has a mass that's 207 times that of the electron, hence the algebraic equation there. And then A clearly is going to be the reduced Bohr radius. So let's see how we find out what to do. Stop. Okay, so if we're trying to find the ratio, we see that we get the reduced mass over the ME, and this is what the reduced mass is, a product over sum for the mass of the muon, proton, and then again we have to divide by me. Cool. This is awesome because when we plug in the mass of the muon, which is 207 me, we see that this denominator cancels with this numerator, and I'm good to go. Now I can also cancel out the mass of the protons by factoring one out, which is seen here, cancel, cancel. At this point, you really don't need to, but it just makes the calculation easy because I only have to plug in 2 mass terms instead of 1, 2, 3, so a little easier. But then we see that we get the ratio of 207 over 207 with the mass ratio plus 1, and we get that that equals 186, with rounding, of course. And then we see that what this actually tells us is that A equals 186 times A mu, the reduced Bohr radius, and then divide over the 186. We get the actual A over mu, or not A over mu, but A mu as a function of A itself. Okay? And all we're trying to do is modify. So what this is actually saying to do is to get rid of whatever the old A was, right, by cancellation. And we'll see how that works out exactly in the next slide. All right, so if we plug in back into equation 7.93, we realize here that everything that gets modified was in the blue. Okay, so we have mu GP E squared, 2 pi MP, and then the mu goes to 207 ME, and then my A mu goes to A over 186. Okay, that's cool enough. But we see that we get everything back in terms of ME and A, but with the addition of multiplying by 1 over 207 and by multiplying by 1 over the fraction of 186. Or if we remember, the ratio here was just 186. So we just get to 186 cubed because we're dividing by a fraction. Cool. And then we divide by the mass ratios here. But because everything in purple led to the delta energy term that we saw, we can just plug that in. And this is the idea, right? The 1 over 207 and the 186 just tells you I'm trying to divide by the old stuff and multiply by the new stuff. So I'm trying to get out of this number what originally made it and replace it with these two numbers. And in doing so, we see that the mass of the muon is 0.183 eV, and that's not bad. And this, of course, came from equation 7.97. So we get through our first checkpoint, which really isn't bad. The next two, we're just going to kind of highlight how to find the ratios for the Bohr radius and the reduced Bohr radius, and then just plug into this form by getting rid of what was making this 5.8 number itself and replacing it with what's new. Let's see how we do that. So for stop 3, this leads us to part B, which is positronium. The G factor gets moved from 5.59, which was the G factor for the proton. Again, we got that from the magnetic dipoles. And then we see that mass of the proton gets replaced with the mass of the positron, which of course has an Me, which we said was equivalent to Me. And then of course we need to change the A to the reduced A. Okay, so let's find our ratio here. Mu over Me, we see that we get the Mu is the electron mass, with now the protons being replaced by the positron. Positron there, cancel Me both top and bottom. But we also see that the mass of the positron is equal to the mass of the electron, so we're replacing that again here. So we get Me plus Me in the bottom, that's 2 Me, and we see that the mass of the E's cancel, so I'm left with a factor here, a change factor of 1/2. Okay, so we take that same idea here, right, from equation 5.97, and we divide out what was put in it to make it and replace it with the new thing. So since we started with the G factor for P at 5.9, divide that out and then multiply in by the new factor 2. Okay, makes sense. Since we had the mass of the electron, divide that out, or the mass of the proton, the 9.11 times 10 to the negative 31, divide that out, replace it with the mass of, or the proton was 1.67, excuse me, and that was in the denominator. So divide that out by multiplying and then put the new mass term here, and then the factor of the Bohr reduced radius is 1/2. okay, and just using the streamline effect, we get that this is equal to 4.82 times 10 to the negative 4 eV. And that brings us through our second stop. Not bad once we have the setup. Take out what's old. So this is old, and this is old, and put in what's new. Okay, so now that we have that down, let's do it for our last one and call it a wrap. So muonium, again, the G factor gets replaced. The mass of the proton goes to the mass of the muon, or muonic, which is 207 Me. A gets replaced as well. Find the reduced mass again. Me cancel, but we see that M of the muonium is equal to 207 Me. Cool. That tells us that we end up with 208 here, right? Because 1 plus 207. Me's cancel, so we get our ratio of 207. Cool. So plug it in the exact form like we had before. Get rid of the 5.9 that was multiplied in to make this purple number. Replace it with the 2. Now we have 207 times the mass of the electron, replacing the proton mass. So multiply to get the proton mass out of the purple number, replace it with the new number. And then we have our Bohr ratio here, which is 207 over 208. We have to cube it. Once we do that, we get our final energy of 1.84 times 10 to the negative 5 eV. And then using this method, we could calculate these, kind of get a global picture or local picture of these electric, or not electric, but the energy terms for these exotic particles. So this was a pretty fun question. A little bit in the setup work and me rambling, but this has definitely been used throughout the book and will continue to be used anytime we're dealing with interactive particles. And you can go back to chapter 5 for that and where we found the reduced mass term in and of itself. I believe it was 5.1, something like that. So go check that out if you want more on the reduced mass term. But otherwise, that's it for this question. Pretty straightforward. All right, so in summary, we got to do a lot and learn about the whole array of particles, which we'll definitely get into in the next one of the next series with particle physics. So we're starting to set the stage here and in the E&M class where we got to talk about all the weird stuff that we noticed. That being said, I need to give a massive thank you to my supporters for making this possible, especially with the travel that I've had recently. It's been quite crazy, all things considered. So definitely thank you for your support. It's making this really helpful. And if you'd like to see more, especially on what I'm going to release this weekend, with the 30-page PDF of the Zeeman effect for an N=3 atom, that was a lot of work and a lot of tables, especially decomposing an 18 by 18 matrix. So that was a lot of fun. 324 elements to break down in the matrix, and the selection rules come through quite heavy. That was fun. But books, notes, and other reference materials are found below, and if you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.